Okay, so we are moving on to a type of bifurcation that can only happen in a two-dimensional system, and we saw that two-dimensional systems have phenomena that we could not get in 1D. All these bifurcations relied on these bifurcations of the one dimension. Now, the added phenomena of the 2D includes limit cycles, of course, and so we can have bifurcations in which limit cycles appear or disappear. Okay, so of course, inherently different from these type of bifurcations. So, and this happens in the following way. If we have a fixed point, an unstable fixed point, for example, in the process of the bifurcation, it may become stable and open an unstable limit cycle around it. Or we could start from a stable fixed point and have, after the bifurcation, an unstable fixed point with a stable limit cycle around it. And this process is called Hopf bifurcation. And to understand how this happens, I want to discuss for a moment what happens to the eigenvalues of a fixed point at a bifurcation. So when we are concerned with a regular node, we have for this regular node two eigenvalues that are real. Okay. Say it is stable. Okay. We have two eigenvalues that are real. Remember, we get them by this quadratic formula. So basically, they're real, and they are equidistant from the tau, the half tau here. And when we have a bifurcation, then one of the eigenvalues should perhaps should perhaps go from negative to positive. Okay, from negative lambda to positive lambda. So imagine that changing our parameter would make these two values diverge until one of them crosses into the positive lambda. So from a regular stable node with two negative eigenvalues, we would go into the situation of a saddle, one negative and one positive eigenvalue, by changing this term. Okay, this might also change, but yeah, it should also change. So we kind of slide this pair and also make it grow more separated, and in the process, we will have one of them crossing into the positive lambda, and we are left with a saddle. That would be the saddle node bifurcation. Sorry, it will not be the saddle node bifurcation. It will be a process where a stable node becomes a saddle. Okay, saddle node bifurcation should be something else. The saddle node bifurcation would be the appearance of some fixed points, and okay, no, it's not for this. It's not this type of bifurcation. I'll leave it. So this is what happens with regular nodes losing their stability. When we have a spiral, the product here is a saddle. Yes. Yes. No, but it's not the saddle node bifurcation. I just mentioned this by mistake.
How does that relate to the limit cycle?
Okay. This is the regular case. The case of the Hopf bifurcation is a little different. In the Hopf bifurcation, we start with a spiral. Okay. So a spiral should look like this. Okay, this is tau over 2. And this is imaginary. So we have plus minus an imaginary term. We have 2 points equidistant from the real axis. And then when we change the parameters of the system, we might have these two going into a positive real value. So the fixed point will lose its stability. Okay? And when it loses its stability, here, this was stable spiral. When it loses its stability, it becomes an unstable spiral. And then we have also a limit cycle around it. What? Is it? Well, no, there is a special case when it is not like that. But why is there a limit cycle? I would think that the dynamics far away from the fixed point does not have to change. Okay, so the dynamics far away from the fixed point is also, it's this, right? Everything goes in. But here, my change of the parameters might have affected only the fixed point, only the vicinity of the fixed point, but far away, things are still going inwards. Okay? Because this is what we do here is a linearization. It holds for the vicinity. The change in the parameter might not have changed this as dramatically as in the fixed point. So this is the way that the fixed point changes stability, but the system retains the behavior far away from the fixed point. And the way I see it, it's a kind of balance that is preserved, similar to what we have in the regular 1D bifurcations. You create a stable and unstable fixed point, right? They kind of balance each other, and have the behavior around them stay the same. Okay. Also in the pitchfork, you have always alternating stable and unstable fixed points. So here, if you lose the stability, you kind of compensate for it by having a stable limit cycle around. And in general, I think we mentioned that a stable limit cycle will always have an unstable fixed point inside it, and vice versa. And if you have concentric limit cycles, they will always have alternating stability, obviously, unless one of them is half stable. So the idea is that we move from a stable spiral to an unstable spiral by a change in the real value of lambda. The way we draw this on a bifurcation diagram is this. We might have our bifurcation parameter mu. So this is our spiral, and at some point it loses its stability, and we have opening a stable limit cycle. Okay, and we commonly mark this on the bifurcation diagram by marking the extremes of the limit cycle, but doing some drawing like this to mark that it's not a pitchfork bifurcation, but a Hopf bifurcation, creating a limit cycle. Okay. So this is how this will be marked in a bifurcation diagram. Of course, you could also have the complementary case with an unstable limit cycle forming. This is harder to find by simulations, the unstable limit cycle, but when you run the system backwards in time, you can have the stability reversed, and then you'll see things converging to this limit cycle. You might have this in your next exercise. Say again? What? This? I don't mind so much. So I don't know. Yeah, it's supposed to be dashed, but it's really. Yeah. Let's see what I did here. Yeah. It makes things a lot harder to understand, but yeah. Yeah, you're correct. It's better this way. Where? This? Yeah, there is only. Yeah. On the bifurcation diagram, it looks like a curve. Okay, this is specifically this is a supercritical Hopf bifurcation because the limit cycle opens for mu larger than mu c. You could have also a subcritical Hopf bifurcation and of both types. I won't draw it. Another thing that you can do when you show just a moment when you show a Hopf bifurcation is show the other dimension of the system and make a 3D plot where the cycles will be exact. They will show us both the x and y coordinates, and they might be even non-circular, of course. And this is very nice. You'll do this in your exercise. Mm-hmm. No. So when you add the other dimension, this could go, out of the board. Okay. Yeah. You do a simulation. You can try to do a Poincaré-Bendixson proof, okay? But that's generally hard. Mm-hmm. Most of the time, yes. Most of the time. So the other. Okay, so this brings me to the other point that I wanted to show. And the case when this does not happen, okay, is when, in this case, you have an unstable, maybe it can happen backwards as well, but you have an unstable spiral. Yeah, it can happen backwards. And then at the bifurcation point, you have centers. You have a center with closed orbits around it, and then you have a stable spiral. This is the special case in which you move from an unstable spiral to a stable spiral, but you do not have a limit cycle opening. Or vice versa. You can move. One of this, you can have such a transition without a limit cycle opening. When will this happen? Because we just So yeah. Wait. Let me start again. The Hopf bifurcation is a bifurcation when you have this transition. You have stable fixed point into to a unstable to stable with limit cycle, or stable fixed point to unstable with limit cycle. The special case is when you move from an unstable to a stable spiral, but you don't have a limit cycle opening. Okay, and in that case, when at the bifurcation point, you have centers. So this okay, so basically I would advise just to do simulations and see what happens here and here. This happens, okay, remember that when we classified the fixed points, we said that sometimes the classification should not be trusted, okay, because nonlinear terms may change the stability greatly. So this is, remember, the case that we classify as centers is one of those cases. So if at the bifurcation point we find that we should have a center, okay, then it's still possible that nonlinear terms dictate a stable or an unstable spiral. Okay, so this case, this is called the degenerate Hopf bifurcation. Degenerate Hopf bifurcation. This case is the case when the classification of a center is indeed valid. Okay, and the nonlinear terms do not matter. They do not change the fact that this is a center. In the general case, at the bifurcation, this is not really a center, but actually a spiral. Okay? Second? What? No, you don't know this in advance. Okay? And generally what we do, we have kind of left the realm of analytical treatments, because when we have limit cycles and later when we are in 3 dimensions, it is very hard to do the analytical treatment, and usually we resort to simulations. Yeah.
You have to have a limit cycle or a center. You cannot have like something like a change in the stability of the spiral. Like let's say it was stable and now it's going to divert.
Yeah, yeah. You can have it, but at the bifurcation points, exactly, there will be centers. Because remember, you need to transition from here to here. Here you have centers.
So there will be center also in a regular Hopf.
If you do the analytical treatment, you might find that there is a center. But what I'm saying is that nonlinear terms should invalidate your classification. So what I'm showing here is kind of phenomenology. Phenomenology? Okay. It's kind of showing you that these things exist, and in saying that it might be hard to recognize them, or to determine that you have this in the system, and usually it will be done by simulation. So I just want you to know the terms, know the Hopf bifurcation, and in the exercise we have a very interesting case of a Hopf bifurcation, which we find and we treat by simulations. Okay, so there are other types of bifurcations that are specific to the 2D systems, And if you want to know them, you are advised to look at the relevant chapter in the book. Just don't have time for it because they want to move on to the 3D systems. And there are kind of special cases. So all these are. It's not essential to know them. Although I will say that I did in my work analyze a system that had one of these special bifurcations. Okay. Okay, we now move on to three-dimensional systems, and when you are dealing with three-dimensional systems, you start having new phenomena. Remember, when we moved from 1D to 2D, we started getting oscillations and also limit cycles. So similarly, when you move to 3 dimensions, you start having other phenomena. You can have new types of bifurcations. Remember here, we had new types because we had the limit cycle and so on. When you move to 3D, then you can have, say, on one axis, a regular bifurcation, and on the other axis, a limit cycle appearing or disappearing. But what we are going to concentrate on is phenomena that are only seen in the nonlinear 3D systems, nonlinear, and these are called, basically they form the theory of chaos. And if you are, okay, so after this lesson, if you are interested to know more about chaos, then I really recommend a good introduction to the field, which is just the book Chaos by Gleich. Actually, he's American. It's probably Gleich. I think it's written this way. So this is a popular science book that explains how the field of chaos emerged and really gives you the stories of the scientists who pursued these investigations, even though it was very unpopular. And the message of the book is that while the classical sciences usually restrict themselves to linear systems, especially in multiple dimensions, to linear systems or to simple cases, or to linearizations, and so on, then a lot of the things you find in nature are nonlinear, and then you have to deal with these types of systems and understand what happens to them, even when they cannot be linearized, and so on. So in this lesson, we'll give basically the classical introduction to chaos, which is the Lorentz equations. Lorentz equations. Now, they were developed by Edward Lorentz, who was studying weather. Okay, he was studying currents in the atmosphere. And he had this model of convection flows. So say you are looking at a column of air, and the sun heats it from below, and you have the ground, the sun heats it from above, and you have the ground from below, and so on, and you have flows of air going up and down. and he reduced his system to the non-dimensional equations that I'm going to write here. Okay, so you have x and y and z that represent different variables in the system. V, if I remember correctly, is the velocity, the vertical velocity, but x and y, I don't remember exactly what they are. And so we have here x, y, and z and different parameters. Sigma is the Prandtl number, and we have R is the Rayleigh number. Rayleigh number. They are constants for a certain fluid. So if you're talking about air, they have a certain value, or maybe they change, for example, with the temperature or so on. R does not change with the temperature. Okay, and B is a parameter. You can go to the article you can find on the web and see what they are exactly, but it's kind of following a nonlinearization, so they are not exactly I think they are not exactly these terms. But they are what you get in the process of non-dimensionalization from these numbers that basically control the properties of the fluid. So a Rayleigh number of the fluid will tell you whether the convection of heat, whether heat is transferred by conduction or convection or by turbulent flows. Okay, so there is a critical Rayleigh number above which you get turbulence, for example, and so on. I should connect my computer now. Is it on, right? No. Can you see anything? Close the lights. Okay. I'm not able to operate this. Yeah. No? It's making noise. Left. What? There. No. Something is happening. Oh yeah. Good. Okay. Yeah. Okay.
Do you want me to try to act?
It's okay. It's here. Okay. Okay. So I have this simulation of the Lorentz equations, and where I choose an initial condition. It will take some time for it to calculate. What? Yeah, eventually we'll get a 3D plot. Oh, didn't take time at all. Okay. Okay, so Edward Lorenz was, he was working in the 50s and 60s, and you can maybe imagine the kind of computers he had to run the simulations on. But in fact, even the level of computing that was available then was a great boost to the field of dynamics and specifically to chaos theory, because as we will see, these things you basically you can investigate almost only by simulations. So he was running his systems for different parameters that he put in, and running them for very, very long times because he was seeing this strange behavior. This is X, and this is Y, and this is Z. And you can see that there are these oscillations. And, of course, Lorentz was trying to find a pattern here. The great hope was that you will be able to model weather and predict what happens in the atmosphere and predict weather more accurately. So let's see what happened with that figure. Okay. So, and it turned out that these outputs of the system are not in fact periodic. Okay, and they do not settle to any fixed point or limit cycle, at least for these parameters, for this parameter range. And when we draw this in 3D, we get this famous butterfly shape. So you can see how X and Y and Z oscillate. Maybe I'll show this. I'll try to turn the display. Yeah, something like this. We have this kind of two systems of rings, maybe like Saturn's rings. One here and one here, and the system kind of alternates between them. And I suppose Lorentz was very disappointed to find that it's not exactly predictable. Okay, when will it switch from one wing to the other, and how many oscillations will it do? What will be the amplitude of the next cycle, and so on. It turned out that this is inherently unpredictable. Okay. Now remember that our system is deterministic. There is no noise in the system. All the special properties here arise from the fact that it's nonlinear. So you see, here we have a nonlinear term, and here we have a nonlinear term. So the nonlinearities in 3 dimensions give us this thing. And what is this? So, yes? Yeah, exactly. So what you have here is right. So you see this initial condition. The system started, and after a transient period, it settled into one of these wings. So what we have here is a plane. Say, let's call it a plane for now. A plane where we have the system oscillating, and it's a kind of double curved plane where the system that the system goes into. And this is called, first of all, this is called an attractor. A fixed point is also an attractor. A limit cycle is an attractor. This is called a strange attractor. Strange attractor. And in fact, what we have here is not exactly a plane. This is something with, you can imagine that it has some thickness, okay? And the oscillations here go on this something that is a little thicker than a plane. And this is also why they can stay here and never cross each other. Remember, we have the existence and uniqueness theorem that says that different trajectories cannot cross each other. And in the 2D system, this is what the Poincaré-Bendixson theorem relied on, that if you are closing into a certain trapping region, this donut, then you must go into a limit cycle. Also because you cannot cross yourself. In 3D, you have space on which you can cross. You can do a loop, and then you can go a little upwards and do another loop, and it can kind of transverse the first loop and so on. So this is what we have here. This is a very complicated system where there's just a bit of room for the trajectory to oscillate infinitely without ever repeating the same loop. And when you do in your exercise, you'll have an analogous system, and you will be able to zoom in and zoom in and zoom in and see that it never actually goes through the same loop. I suppose it can be a volume. I'm not sure. So the Lorentz Strange Attractor has a fractal dimension of 2.05 or something like this. And this means that it's not exactly a plane. It's just a little more than a plane. And if you want to know about fractal dimension, there is a very good chapter in the Stogas book dedicated to fractal dimensions, which are basically, they deal with shapes that are they're not of a dimension of 1 or 2 or 3. They are something in the middle. Okay, so I really recommend that chapter in the book. If I had time, I would have covered it as well. Yeah, sure. When you analyze a system, you want to be able to say, okay, if at time 0 it was here, then at, say, infinite time it will be there. Okay, you would like to say what happens at each point in time, right? So you would like to be able to give an analytical solution to the differential equation and so on. But in this course, we cover the field that is concerned with systems that you cannot solve analytically, but instead you are satisfied with saying what happens at infinite time. Does it go to a fixed point or limit cycle? And where is this fixed point? With limit cycle, it's a lot harder. And so in this system, you would like to be able to say, okay, the weather started here, and I want to know what will happen eventually. Will it settle down? And where will it settle down? But here you cannot tell, okay? You have this strange attractor. As far as you're concerned, at infinite time, it can be anywhere in the strange attractor, okay?
This way you do know what will be in like 10 steps. You just don't know what will happen in infinite
Okay, so when we move on, I'll you'll understand why you're not even sure what will happen in 100 or 1,000 steps.
Yeah,
Okay.
because over here it seems as if you can
Yeah. It
every step
exactly, but you will have to do a detailed simulation. Okay.
in order to see that
Yeah.
it's not.
And basically, the implication of Lorenz's findings is that if you want to predict the weather, you have to do a detailed simulation of the atmosphere of the Earth. And and exactly, and it turns out that you need to it to be infinitely detailed without any error in order to predict exactly. Okay, and I'll cover these principles as we go along. Okay, so let's give a definition. If I write here, is that okay? Let's give a definition. Okay, chaos is defined as aperiodic long-term behavior in a deterministic system that exhibits, and this is important, sensitive dependence on initial conditions. Okay, this is a bit small. I'll write it bigger. So, okay, so aperiodic means that it does not settle down to fixed points closed orbits or quasi-periodic orbits, which we did not cover, but you can find it in the book. It's not so important for basic understanding of the field. Okay, deterministic. Sorry for the mess. I'm avoiding the projector. Deterministic, meaning no noisy inputs or parameters. So the irregular behavior arises only because of the nonlinearity. Okay, this is also important. It means a lot of times when you analyze a system, you say, okay, there are things that I don't know how to predict. There is noise in the system. Maybe there is something inherently stochastic in the system. So I'll add it as a term that is stochastic, as a random noise. And then you find out that there are things that you cannot predict, or you cannot be exact in your predictions. But what we are saying here is that even if you know everything to the finest detail, you will not get the periodic behavior. You will get aperiodic behavior. Even if you know everything to the finest detail, you will go to the strange attractor, and it will be very hard to tell where the system is at every time point. You have to do a detailed simulation. This is unlike a limit cycle, where you are restricted to this curve in space. Okay, and sensitive dependence on initial conditions means, okay, I don't have space, so I'll write it like this. Sensitive dependence on initial conditions means that nearby trajectories separate exponentially fast. And we have to take a break, so I'll just show you the plot, and then we take a break and start discussing this plot. So okay, so what I did here was start the simulation from an initial condition that is removed by 10 to the minus 10 from one of the from the previous initial condition on one coordinate. I think it's 10 to the minus 10. Let's see. Delta, yes, 10 to the minus 10. Okay, so you can see that initially the trajectories overlap, but then they start diverging and they start behaving very differently. Okay? And when we see this on the 3D shape, then you see that the green system that was removed by this amount, by this delta in its initial condition, is already doing different things. What? Well, it's still restricted to the strange attractor, yes. But within the strange attractor, I don't know what it does. Okay. Yeah, so at least we have the strange attractor, right? Yeah. No, this is one strange attractor. It's considered one strange attractor. It's just kind of folded. Okay, so next period we'll see this.
For these 2 points, they will be
Any.
And it doesn't matter if they're very far in the initial condition? Initial conditions are very far. Does it mean that it'll be more, like, further?
No.
No?
Not really, no. No. You'll understand this in the next lesson. שבנקודת זמן מסוימת הכחול יכול להיות פה והירוק יכול להיות פה.
רק הצורה הבנתי.
באמת יש איזושהי מגבלה על כמה רחוקים הם יכולים להיות.
לא, כי הייתי אומר, אני אקח נקודה רחוקה מהכחולה והירוקה. אני יכול לחשוב את זה כאילו, במקרה הכי גרוע.
נכון, כן, דברים פה לא מתפוצצים.
זהו,
זה בתוך הסטרנג' אטרקטור, אבל אתה עוד, כלומר, לפעמים אתה לא מסתפק, כלומר, אתה היית רוצה שמתנהל כלל קרובים, אז לפעמים אתה מתנהל מתוך כלומר, קרובים. במערכות ה-2-dimensional, כן, זה מספיק. במערכות שהן 2-dimensional, זה לא ככה. כלומר, טוב, יכול להיות לך אולי שהם נכנסים לפאזה שונה באלמנט אולי. אני מניח שכן. אבל עדיין,
ועדיין, טוב, לא מבין למה ליניארי לקשר מחוץ לזה.
למה חוסר לינארית?
כאילו, לא ליניארי.
במערכת לינארית, אתה מקבל רק נקודות שלה. אתה לא מקבל אפילו באמצע.
שעדיין היה...
זה עובד בינתיים,
אני כבר הבנתי שאי
מביאה
אפשר
שוקולד
להביא.
והיא מבקשת אננס.
מה?
זה בסטייל, לא פותחים אותה פה, אנחנו מבקשת אננס. היא רואה שאני שותה ביס, אז היא אומרת, תביא משהו, תביא לי מים. לא תמיד עובד.
אני לא יכולה להגיד לא.
מה? יש לי פולשות ממנה, אתה...
לא, אז תשפרי אותה.
לחסוך את זה ממנה. אבל אני כבר בן אדם מבוגר, כלומר, היא לא חלק, אפשר יותר... זה לא... מה? אתה רוצה שהילדים שלך יהיו יותר ממה שאתה?
אני רוצה.
לא תמיד את יותר ממה שאתה. בואי, בואי לי לעשות ככה. כי בא לי עושה ככה, הוא בא אליי ועושה לי... זה לא עובד אצלי ככה. אוקיי.
שבע בעלה.
כן. בטוח.
תקשיב שנבנה לך. לא יקרה? לא. לא קונה לך אותה. כן? לא קונה לך תלמידים מתוך עיקרון כאילו או סתם?
לא נורא מדי.
זה לא שורק, זה מעבדה ניסיונית, זאת אומרת המעבדה... המעבדה שורק, נצטרך להרחיב אותו. להגיד נגיד הפקידים שלו. כן?
שירה היא ולרדת.
כן, בדיוק. רצים אחרי זה, אני
מעדיפים את זה לך משהו שנגעת בו, אבל לא עובד לך את זה.
טוב, מה זה?
לא, מה שהאדום טיפה.
לא, כן, אבל מה עם השרדה הזה?
טוב, לקחת את הכלום הזה מטוב? אני יכולה לעשות את זה. שתיים, אני יודעת שיש שיעור.
טוב, צריך שמדעים פה, לא לעשות את זה מול העיניים שלנו.
אתה יודע, אני רוצה לשאול סיבה כי יש לי פגישה עם משרד, אחרי שאחרי שבא
יהיה כמו לעבור שוב על אותה פגישה.
לכתוב שוב פשוט לשנות
יש
ולוודא תגיד, שתי השאלות האלה,
במערכת.
אותו דבר? רק כי היא אמרה לי למה זה 3 וזה 4?
באחד יש חזקת סבירות.
כי היא רשמה, היא אמרה שזה אותו סבירות, כי כבר שינו את זה וזה כבר לא 4.
יכול להיות.
זה פשוט, אני חושבת שאולי זה מאוחר יותר, ואז כבר לא, אז יכול להיות שהפעם אנחנו להיות מקדמים. לא 4.
נכון.
זה עדיף. פחות מעקב, פחות פחקים, פחות סבירות. היא אמרה, דרך כלל פתח אנחנו לא מאוד להשאיר לך יותר על כל הדברים ש... כן, אז זה אומר שזה...
טוב שאמרתי גם.
כי אמרה שתלוי איפה. כי אמרה שהחוקרים אמרו להם שכאילו, אבל הם חושבים לחיים נורמליים, וכאילו לא צריך באמת את המעקב הארוך הזה.
אוקיי. אז נעשה את זה. Okay, so we were talking about how initial conditions that are very close apart, very close to each other, might diverge from each other. And the idea is that at a given time, remember we are talking about long-term behavior. After a given long period of time, then the system that is marked here in blue might be here, and the system marked in green might be here. Okay, so we are concerned because after a long time, the systems might be even at different edges of the limit cycle of the strange attractor. Of course, they are still constrained to the strange attractor itself. So it's not like very similar initial conditions just go to negative or positive infinity. This is not what concerns us here. So we measure the divergence of nearby trajectories by looking how this delta, the difference between their initial conditions, grows. Okay, so basically it's as if we start from a certain initial condition, this point in space, and then we start with a very, very close initial condition that is removed by a vector delta. So x plus delta where delta is initially something very small, like 10 to the minus 15. And then it turns out from the numerical simulations that the Lorentz equations have this delta, or its absolute value, grow exponentially fast. Okay, so delta 0, the initial value, times e to the lambda t, where for the Lorentz equations, for the parameters that I ran here, lambda is about 0.9. So this is growing. Okay, it's not as fast as e to the t, but it's growing. And I think, yeah. See? Okay.
What are we characterizing with these things here?
The separation between one curve and the other that started very, very close to each other. So they started, say, from 2 points in space that are removed by a delta that is 10 to the minus 15. Okay, so they are very, very close. And we are measuring the separation between x of t and this thing, or the other trajectory that started from that delta. Okay, so the delta is a separation between the two trajectories, and we are looking at it across time.
Okay, so and the lambda that we get,
Yes.
what does that represent?
the lambda that we get? Okay, you'll see right now. Okay, I'm saying that this is what they found for the Lorentz system, and we'll see how this is found. Okay, so here we have this logarithm of delta with time, and you see that it's oscillating. Okay, so the systems they sometimes oscillate compared to one another, or they change the separation, but in general there is a trend that is almost linear. Okay, so a very general linear trend until they get to the order of 0. Okay, so when the logarithm is 0, then the separation is order 1, right? And then these oscillations are probably the two trajectories being on different wings or different parts of a cycle within a wing. Okay, so these oscillations are probably being on different sides of the butterfly. Specifically here, so this might be the largest separation available in this strange attractor. Okay, so what we have here, remember, this is logarithm of delta as a function of t, okay? And this is linear. If we take the exponent, we get that delta goes as exponent t. Oh, sorry.
Isn't delta the initial condition?
Delta?
Or
No, delta is the difference between the two initial conditions.
how are you measuring the difference? Is it like Euclidean distance?
Yeah. So you could do this. What I plotted here, if I'm not mistaken, is the delta in x, and I can also plot the delta in y and the delta in z, and they all behave the same. This is what I'm trying to show you here. They behave very similarly. They all increase at this general rate. Okay. So if I do some linear approximation of this, okay, logarithm of delta goes as t, so it means that delta goes as e to the power of t, and this slope here, this slope we call lambda, and it goes into this exponent. It controls how fast is the exponential divergence of the deltas. Okay.
Why is it that the behavior is essentially the same for every direction? Is that like a property of this particular system? Or?
In this system, yeah, it is. Mm-hmm. Here, this is when logarithm is 0, then the distance is order 1, and if we look at the strange attractor, I want you to see the units. Okay, so you can see that units here are order 10. Actually, here it's not really 0. See the units here. It's above 0. Okay, so logarithm of, I don't know, almost 3. Okay, might be the largest separation that you get. So the idea is this delta is called the Lyapunov exponent. This lambda. Sorry, lambda is called the Lyapunov exponent, and it measures how fast is the exponential divergence of initial conditions that are very close to each other. And in your exercise, you'll be required to find the Lyapunov exponent for a different system. And this is how you do it. You mark a line on the plot and you get the slope. Strictly speaking, you can get a Lyapunov exponent for each of the dimensions in the system. Lambda k, lambda x, lambda y, lambda z. And when we ask whether there is sensitive dependence on initial conditions, meaning do we fulfill the criterion for chaos, we look at the largest Lyapunov exponent. Okay? Now, this was started from a certain initial condition, okay? And then we removed a little from it. If you would like to be very rigorous, you would maybe do this thing for different initial conditions in the system, say 10 or 100, and then average the Lyapunov exponent that you get. But as you see, the passing of the line here is also, I do it very roughly, okay, and I don't expect you to do a regression on this, okay. You can do this very roughly by eye, so it doesn't really matter if you take a lot of initial conditions. You just want to get to know a rough estimate of the Lyapunov exponent, and what is important is whether the Lyapunov exponent is positive or negative. If it's negative, it means the initial conditions converge, okay, say to a fixed point, or, okay, I'm not sure what will happen on a limit cycle. But, yeah, I think you'll get a different slope. When lambda is positive. And you'll see, actually, also in papers in neuroscience, in theoretical neuroscience, you'll see that when people are asking whether a theoretical neural network is chaotic or not, they show you the Lyapunov exponent. And they show you, okay, when I change the parameter, at this point, the Lyapunov exponent becomes positive and the system is chaotic. So some people say that neural networks needs to operate on the edge of chaos, not with a small Lyapunov exponent, but not with a big one. Okay, so going back to what this all means, a positive lambda means that there is some time horizon beyond which it is very hard to predict where the system will be at. So, and going back to what I said before about trying to predict weather, and this implication that you need to do a detailed simulation of the Earth's atmosphere, okay, then when you try to simulate a system, or say you would like to simulate the Earth's atmosphere, and you will base this on measurements taken at a certain time point, you will always have an error of measurement, okay? And this error of measurement, even if it is very small, it could drive very large errors in your prediction, okay? So you see, after a long time, these will be the errors in the prediction. So it almost doesn't matter how accurate is your measurement. You will always, at some point, you will always go to these large errors. And say we are willing to tolerate some error A, okay, then the time horizon will be of the order of 1 over lambda logarithm of A over delta 0. Okay, so say delta 0 is 10 to the minus 15, and A is 10 to the minus 1, okay? This will give you 14, okay, out of the logarithm. So 14 over delta. So the time horizon is 14 over lambda, 14 over lambda. And the time horizon will always be some small, not very large multiple of lambda. And lambda, we know this is 0.9. So after several tens of time steps, you will already not be able to predict the system. Predictions break down. Order. A is the error that you are willing to tolerate in your final prediction. Okay? So say A is 10 to the minus 1, so it will be around here. And you can see you reach it after 25 time steps. Sorry, 25 units in time. It's not the time steps, it's the units of dimensionless time. And this also shows you that lambda is a time constant. As you can see here, it multiplies t. So 1 over lambda is a time constant of the system. And basically, it's a time constant, and the horizon time is a small multiple of this time constant of lambda. Because in my simulations, I don't take dt equals 1. I take dt equals 10 to the minus 4 or so. Okay. Each dt is a step in the numerical simulation. And I try to make it as small as possible, remember, and not have... yeah, as if it's not discrete, exactly. But the units of time are not dt, they are these. Okay. And this has to do with the non-dimensionalization, for example. And you want your dt, remember, to be at least an order of magnitude smaller than the time constant of the system. And what is the time constant of the system? So here, say, take the x equation, the x dot equation. Here, you actually have the time constant of the system. So a lot of times you have equations looking like this. X dot equals 1 over tau. This is the time constant. And you have some expression here. So here, 1 over sigma is the time constant. And sigma is around 0.8 for air. 1 over 0.8, that will be 1.25. So that's your time constant. So dt. The parameters, they are dictated by the physical system. So, yeah. If you're interested in the book, they show how the system behaves for different ranges of parameters. I don't remember which one they take, maybe R. And they show that this chaotic behavior occurs within a certain range, and at a different range you just have a fixed point or two fixed points, and at another range you have these what's called a saddle cycle. It's something that you didn't see in the 2D systems. It only happens in the 3D system. Okay, let's go on. I'll just say that the implication, of course, is that you cannot generate a good prediction of such a system, of a 3D nonlinear system. Okay? After this amount of time, your prediction will break down, and you'll be dealing with this kind of errors, which maybe in some systems you will tolerate them, but for predicting weather, it's probably not good.
I'm just trying to get an understanding of what the magnitude of the error really, like those look relatively small.
What?
when
These.
no, I mean those are definitely wrong.
Yeah.
Right, but like even once you pass the time constant.
Yeah. So
Yeah, but it's like ln of 2, right? So that's not
so
such a big
yeah.
difference.
So look at the scale here. So minus 20 is 20. So what we are saying here is that after this amount of time, the difference between the systems can be this. You see this? Okay. So because you had a very minute error in measurements, your prediction for time 28 might differ by the largest distance possible on the strange attractor.
But it's not like a super insane error. It's like
It's not super insane because the system does not explode.
right.
Okay? Yeah.
Okay.
Okay. I'm going on to define an attractor. Okay. An attractor we define as a closed set A that is, it has several properties. First one is it is invariant. Meaning that any trajectory that starts in A stays there for all time. So trajectories stay in A. They start there, they stay there. You can already think of several entities that fulfill this. Okay. It's attracting an open set U. It's an open set of initial conditions. Just to be exact, or to be more clear, conditions. So this is a property, and the explanation is that there is an open set U that contains A such that if x at time 0 is within U, then the distance from x of at time t to the attractor goes to 0 at infinite time.
I didn't quite get you. What do you mean first by when it starts in A, it stays there all time, the trajectory? I didn't get that bit.
It means that things don't go out of it. So an attractor is an entity, closed set, that trajectories cannot go out of.
Okay, so you mean that it's not that the trajectory. Okay.
Okay.
Like for example, like limit cycle.
Exactly.
For example,
Yes.
invariant.
Exactly.
Okay.
And the second says that things go from outside of the attractor. Things go into the attractor from a certain basin of attraction U. Bound the attractor? Yeah, I think so. Okay, yeah, and the largest set of these initial conditions is A's basin of attraction. Third property is minimal. I don't think that anyone has bound the Lorentz set, analytically or anything. the Lorentz strange attractor. I think theoretically, what?
You know it's not infinite,
Exactly. Yeah. Yeah.
no one gave a number.
I don't know, but maybe. I don't think so because the treatment is not analytical. I'm pretty sure it's not an analytical treatment. I don't know. Minimal. There is no proper subset of A. There is no proper subset of A satisfying the above conditions 1 and 2. Okay. Now, a strange attractor has the added property of sensitive dependence on initial conditions. And often, strange attractors are also a fractal set. Often, they are also a fractal set, meaning that they are not a plane, but something a bit thicker than a plane, or so on. Sensitive dependence on initial conditions. Okay. I just didn't want to spend the time to write it. Okay, let's see. I have two more properties of the Lorentz map, of the Lorentz system that I want to show. And yeah. Oh. Okay, your exercise is for 2 weeks from now. So the last section or so of the exercise we may cover in the next lesson. Okay, so let's turn on the projector. Okay, so Edward Lorentz observed that there is something that maybe it takes a very long time for this projector. There is something that looks almost regular in his set. I'll just draw this. So when you look at the strange attractor from the side, oh, good. You have these two lobes, right? We saw this, something like this. So and it looks as if there is some dependence between the between the amplitude on the z-axis of a loop or a spiral and the point at which the next one is entered. So let's do this. Yeah. So you can see this. Look at the peaks here on the z-axis. Okay? It looked to him like there is something regular here. And also the amplitude of this biggest one and the next amplitude here. So what happens here is that the system spirals in one wing of the butterfly, okay? and it's doing these larger and larger loops. And finally, it goes to the other butterfly where it starts from within and goes out. Okay? And he thought there is some relation between this and this, and this and this. Okay? There might be some general rule here. And let's see. Hope this works. Okay, we can wait, and I can also draw this myself. Let's see. Okay. I'll do this here. Maybe we'll get the plots in the meantime. So what he did was he plotted the maxima. He took the maxima on the z-axis. Okay, we have this thing. This would be zn. This will be zn plus 1. And he plotted them one against the other. So for each zn, you could say what is zn plus 1. Oh yeah, it's taking so long because you need to collect many of these in order to actually see the regularity. But what Lawrence found is that these points... Pause. Okay. There. Exactly on time. Okay. What he found, let's erase, was that these points scatter along this kind of curve. Yeah, it doesn't say. Okay, so this is Zn plus 1, and this is Zn. So for each maximum in the oscillations on the z-axis,
You looked at what's the next step.
exactly. Okay, these are these maxima. For each one, he plots this on x and this on y.
Only maximum, not necessarily.
Yes, exactly. Yeah.
Between Zn and Zn.
We don't care.
Oscillation.
Yeah, it's doing a loop and it's going back. Okay.
What are n and n plus 1 if you have... They're not...
Just a moment. Just a moment. Oh, good. Okay. There. Right. Okay. These are these things here. Okay? The maxima on the z-axis. Okay? So the idea is that from this thing, okay, you are going here, for example. And these, remember, we saw they kind of increase. 1, 2, 3, and so on. Kind of increase, and then go and start again from a low value. And increase, and then go to the other low. And, okay, so this plot is called the Lorentz map. You will also be required to do one such plot in your exercise, I think. And it turns out that the points here scatter along this curve, only it's not really a curve. Again, it's something that's a bit thicker than a curve. Okay? So it's not as if I can give you a rule, a definite rule. If Zn was this value, then Zn plus 1 would be that value. Okay? There is some thickness to this curve. But still, this is very useful. It gives you another rough, something that I can say roughly about the system. And one thing that is significant here, you see that I plotted the diagonal in black. The slope of this map is always larger than 1. Also, this negative slope is smaller than negative 1, as you can see by comparing to the diagonal. And this is actually quite a powerful result because the system is aperiodic, okay? But still we see that its periods obey a certain rough rule. The final thing I'm going to do is show you how we can analytically rule out. Let's preserve this. How we can analytically rule out the existence of limit cycles in the Lorentz system. Meaning, one can ask, how do we know that this strange attractor is not just a very slow settling to a limit cycle? Okay? Maybe it takes you a really long time to go into the actual limit cycle that is existing there. Okay? And in the meantime, you do these strange things, this aperiodicity and so on. So this is our map. And I noted how the slope of the map will be called f of z. The slope in absolute value is always larger than 1. Okay, so if there were a stable closed orbit, then z must start repeating after some p, which is a number of cycles. Okay? So this is a bit different from what I was saying just a minute ago. There is also the option that this is not a very slow settling to a limit cycle, but actually a very complicated limit cycle, like a rubber band that you would fold and fold and fold again. Say you fold it 1,000 times. So maybe we won't notice this on the plots that we have. But maybe after 1,000 steps, it will start repeating the same pattern. And we can actually prove that it does not. So this means that for some p, some period p, which is a number of cycles, of a number of small cycles here, okay, we will get z of n at n plus p equals zn. There might be some p. Now, we consider a small deviation. As usual, we call it eta. Sorry, we are in discrete steps here, so eta n. So eta n plus 1, if we do a linearization on this curve, we will see that eta of n plus 1 should be what? What eta